But on this stage, I want to welcome Joseph and David from O of1 Labs, who are going to talk about spicing up your ZK with kimchi.
Hi, everyone. So it's me, David, and I came here with Joseph.
Hello.
We work for O1 Labs, and we came to talk about kimchi. Oh, I'm going to take this. Kimchi is the zero-knowledge proof system, which is part of... OK. Oh.
Wait, David.
We have another one. All right. Kimchi is part of Mina, which is a cryptocurrency. It has a lot of cool stuff, which we're not going to talk about, so make sure to check it out. We're only going to talk about Kimchi, which is this small cog in the machine, and that's our zero-knowledge proof system.
OK. To set the context, what do we use it for in Mina? It kind of drove our decisions and things like that. So on the one side, we use it for the succinct blockchain. And in that kind of setting, what we do is every block has a zero-knowledge proof of the state of the blockchain at that height. And then it has the verification inside of that proof. There's a verification of the previous block's proof. And the other thing that we use it for are ZK apps. These are new zero-knowledge smart contracts with privacy. OK, and the kinds of things we're doing in our proofs are what you might imagine, verifying Mina transactions or Mina blocks, but also now ZK app state transitions. OK, so where are we going in this presentation? Well, we're going to start with an overview of Kimchi and Mina. David's going to present that. Then I'll talk about what Kimchi is exactly as a proof system. And then we're going to deep dive into an interesting part of our proof system called the expression framework. And after that, we're going to close with some remarks on tooling and a cool specification framework that David built.
Cool. So to put things in perspective, I'm just going to use that. To put things in perspective, so before we even get to proving things, we need to write circuits. Today we have Snarky. It's an OCaml library that you can use to write circuits for our proof system. Snarky is written in OCaml, so not everybody knows OCaml. It's kind of hard to use. That's what we use for Mina. But we're also coming out with Snarky.js, which is a TypeScript library that you can use to write circuits using TypeScript. So it's much more user-friendly, and we encourage people to try and use it and see if they like it. And once you have that circuit, basically what Kimchi comes into place, you can compile that circuit down to a prover index that you can use to prove the execution of your circuit, the correct execution of your circuit. And on the other hand, you can also compile it to a verifier index or verifier key, which you can use to verify the proof. And so Mina is also coming up with ZK apps, so this is our zero-knowledge smart contracts. And so in that sense, it's not out yet. I don't know when it's going to come out, but I think there's a timeline for it if you're interested. But basically, you'll be able to write these TypeScript smart contracts and deploy the verifier index part on-chain so that people can verify your proofs, basically.
OK, so what exactly is Kimchi? It's a PLONK-ish protocol. So we use the PLONK arithmetization and the protocol. We use lookup as well. For the commitment scheme, we're using bulletproofs. So it's a trustless setup. So there's no toxic waste or anything like that, which is quite cool. And for the recursion, we're using a Halo-style system that we call pickles. And of course, that system needs special elliptic curves. So we're using the POSTA curves. Next slide. OK, yeah, just as a reminder how PLONK is. In PLONK, the circuit is basically a bunch of gates with coefficient parameters. And then the witness is connected with wires, like different parts of the witness or gates like that. And in Kimchi, what we've done is we've extended this to the witness to be 15 wires. And we've kind of divided these into two kind of groups. There's what we call I/O registers. And these can be connected with wires and use a permutation argument. And then on the other side, we have temporary registers, which cannot. We implement a lot of custom gates. So, next slide. we have a Poseidon gate to do the Poseidon cryptographic hash function, which is snark friendly and great. We also have custom constraints for elliptic curve operations and even cha-cha encryption. And that last one, we're using lookup to implement it. Next one.
Cool. So we're switching and we're going to talk about something else. So you're going to animate kind of a picture of what we're doing with like, it's a Plonkish protocol and or ultra Plonk, some people call it. Now we're going to talk about some part of the implementation. Cool. So basically this is a visual representation of every time we try to write constraints for our protocol. So custom gates or lookup was pretty involved also. And we ended up with code that was really hard to understand and write and review and maintain and etc. So we thought we had to like fix something. And we came up with this expression framework, which basically makes it easier to write these constraints and read them by creating this intermediate representation that you can use to, pretty much write these constraints. So I guess we're going to dig deeper on that. You might think that it's not super important, but it's actually a big part of our implementation, and it allowed us to make a lot of progress pretty quickly. So let's look at an example.
Okay, I'm going to take you through an example. So if you have experience with writing custom gates or things like that, you'll kind of maybe be familiar with some of what you're going to see. But the idea is just to motivate why we wanted to make this abstraction. So even for a generic gate, the code is quite complex. So on the top, you have actual code from our proof system. And it's the code that corresponds to the PLONK generic gate. And we have the equation for the constraint below. So let's have a look at what's happening here, what the developer is having to do, and all that code above. It's actually not important to read the code. I'm just going to highlight to give you the idea. But essentially, the obvious things, the code needs to reference the selector polynomials. And you can see that here in red. But what we notice is that there's really no mapping between the code and the equation. It's not even clear. The number of places it's referenced is only 3, but it appears all over the place in the constraint. And it's similar for the witness polynomial here, like it's referenced like 5 times in the equation, but there's just these 3 weird references to it in the code. So even that doesn't seem to line up. Beyond that, we see things like this, where the developer's having to get into kind of proof system details and worry about separating the constraints. So that would be separating this constraint from like others in the system. And in fact, he's having to choose like a specific mechanism to do that, so the powers of alpha. And what's interesting here is that, as you can see from the equation, this is not even part of the real constraint. It's something wrapping around it. So that's not really desirable either, to have to be concerned with those things when developing a gate. The next thing is, all over the code, the developer is like having to specify which evaluation domain to use, and even in this case, switching domain for an optimization to make the code faster. And that's kind of not great either, because those things are really kind of could be done by the proof system automatically. So so the first problem, just very obvious thing, the implementation doesn't closely resemble the constraints. And the second problem, the gate developer needs to deal with all this proof system stuff that really shouldn't be concerned with. And finally, if you want to do optimizations, they're manual and you have to do it for every gate. But it would be really cool if we could somehow abstract that and do it automatically. So basically what I just said, too many non-essential concerns, manual and error prone. So this was a problem for us, and it's something that we wanted to make easier. And our idea for that is this expression framework, which we're now going to try to explain. So David's going to show you what happens to all this code using the expression framework.
Yeah, so basically the code on the right is what happens if we use the expression framework. And as you can see, it's much less code than it used to be. So that's the biggest plus. And if you look at it, the first 3 lines are just like helpers, so it's not too important, but basically we're setting up variables in our equations. And then you have the final equation, and here again, we don't care about powers of alpha to like separate constraints or anything like that. Sorry, that's the zoom. Wait. Is it working? Yeah. Yeah, so if you look at it, it should look pretty close to the PLONK equation that generate gates with the witnesses and the selector polynomials and things like that. If you don't know PLONK, maybe that doesn't make sense, but right.
Sorry.
Oh, yeah. I guess let's go to the next slide. All right, so how does it work? That doesn't work?
We're going to describe now how it works. We don't know how that works. But, OK, so yeah. The essential thing that's going on is like software engineering. We're separating concerns. We identified a place in the system where it just doesn't make sense. So we're separating like the gate developers' concerns from proof system concerns. And from the gate developer's perspective, it just makes things easier and the code cleaner. From the proof system's perspective, we actually get something there too. We get the ability to call into this expression framework and get things the prover needs or the verifier needs. Yeah, so how does that work? Well, we have a symbolic multivariate polynomial representation. It's like an intermediate representation. So you're able to write this code, and you can think of it like an AST or something like that. And then we have a system behind it. Terrible at this. Yeah, and OK, and then there's a system behind it, separate, that is able to interpret it and then process it. So yeah, so there, we have Kimchi here in like this subsystem called the expression framework. And so you define your gate. It goes into, it becomes represented with expression. And then the expression framework can do different things like the constraint separation. You can switch evaluation domain. And interestingly, it can also do optimizations on the expression itself. And then on the proof system itself can then call into it for things that it needs to do. So it can do, call into it for linearization for the verifier and approver, and it can call into it during proof creation to get evaluations. And now David is going to talk about the actual abstract representation.
Yeah, so just to give you an example, if you look at the PLONK generic gates, or the normal gate of PLONK, you have this expression, and if you zoom there, you can see how we write this expression in this abstract representation, in this tree. And you can see that different nodes are just operations between these variables. We have the witness, the coef here is just a selector polynomial. And with this tree, then we can do whatever we want. So maybe one example is that when you linearize the protocol, so linearization is a part of the PLONK protocol. One thing is that you cannot multiply commitments together because we don't use pairings. So here in this tree, the multiplication on the right would crash at runtime or when you run your protocol if you don't evaluate one or both of the variables in the coef and the witness. So in Kimchi, we evaluate the witness. But basically, with that protocol, we can kind of, I think that's fine. Yeah. 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 So basically, with this framework, we can kind of play around and decide to evaluate the coef and see if that works, or decide to evaluate the witness, see if that works. If we have a crash, we know that we didn't do the linearization correctly, and we don't have to deal with we don't have to dig too much in the equations and figure out, because we have many gates, what is missing, what evaluation is missing, etc. And then we can even try and decrease the number of evaluations we have in the protocol and these kind of things. Yeah, optimization. So we cache some nodes also, so we don't have to repeat operations. So it's quite practical. Combining constraints, we've talked about it, I guess. And yeah, we're thinking about future optimizations. There's a lot we can do with this intermediate representation. We could just automatically cache things and not do it manually. We could simplify. We actually use a lot of this to generate code. And so we could simplify the way the code is generated to decrease the number of scalar multiplications or things like that in the verifier circuit. So yeah, there's a lot of things we can do there. Cool. So other features we haven't talked about, but that are quite interesting also. So we can generate LaTeX. We can print the LaTeX, basically, all these constraints in LaTeX. You'll see that again later, but it's helpful to review constraints that we write. We generate also a lot of OCaml code for the OCaml side of our protocol, so it's quite useful for that as well. We don't have to repeat a lot of code. And finally, tests are very easy to write using this expression framework. Like we managed to delete a bunch of code, so that was pretty nice. Cool. So yeah, that's the summary, but I think we don't have too much time, so let's keep that.
Okay, so back up to the Kimchi level, the whole proof system. We have a lot of things that works in the pipeline. So one is a foreign field multiplication gate, which would allow us to hopefully move forward and do things like verifying Ethereum signatures or Bitcoin signatures. That's one of the crypto primitives that we need for that. Another, also related to the same goal, is Keccak 256 gate. So more custom gates. Another area of interest is exploring kind of VM or bytecode kind of based system to try to see if we can plug that in. And we're thinking about rolling our own, but we don't know if that makes sense when to introduce another system like that when we already have a couple really good ones. So
also, I think Caro has some licenses issues, so we're not sure if we can actually use it. Maiden is pretty open for us to use it. So yeah, we're not sure if there's like some issues there also.
Yeah, and we've done some research with Cairo, and there's another talk on the breakout session about that. So if you're interested, go check it out. Again, kind of related to lookup, we've been looking into like different types of tables. So runtime tables or custom lookup tables. It seems kind of interesting for us. And David mentioned earlier that there's code gen for OCaml code, but Kimchi itself is all just Rust. The OCaml code is for kind of the Mina code side of things, because Mina is written in OCaml. And some of that code, we actually would like to move across to Kimchi, and the specific things are the circuit framework and the recursion support. We actually have someone joining us soon to start that work. Okay, yeah, so what David mentioned earlier, we have these cool tools to kind of visualize things. So we have a framework that allows you to visualize a circuit. It shows you the gates, the wiring, the coefficients, and the witness. It just can make it easier. And we also have the ability to visualize the constraints themselves. I promise it is actually LaTeX, it's just there's some big numbers there.
And another thing we came up with, so our protocol was getting quite complex, and we're doing tweaks here and there. And also, as we added more complex features in the protocol, like lookup, it was kind of hard to kind of follow that. So we didn't have a spec also. So we kind of came out and wrote a spec. So I'll put the link at the end, but basically we have a spec that looks pretty nice. We have some protocol diagrams and things like that. But also we wrote that spec using a tool that we wrote also called Cargo Spec. And that tool allows us to extract parts of the code to create the spec. So for example, here on the top left, we wanted to show kind of like what does a proof looks like. And we just extract the data structures from the code, and like that, if we change the code, we still have an up-to-date spec. And on the bottom left, this is my favorite feature. I was a consultant in a previous life. And basically, usually what you do is that you look at a spec and you kind of like go back and forth between the code and the spec, and you check if there's any divergence, and if there is one, then it's a bug. And so we have we have the algorithm pretty much here for proof creation, but these steps are extracted directly from the code. And so you have the code here, and the steps are basically special comments that we can extract. And so here, if you want to review that code or understand how it works, you can just read the code, and the spec is in the code itself. So it's kind of a cool thing if you've been in security and you see that. Cool. So final slide. We have the code on that repo. Contributions are welcome. We want more people to use it also. We're doing a lot of effort to make the API more usable and friendly. So if you want to use it, please talk to us, and we'll spend the time to talk to you and make sure that you can do what you want to do. We also created a book, a Mina book. We call it the Mina book, and we have a lot of foundational stuff on like groups, fields, zero-knowledge proofs, and so on. So if you want to learn, you can go there. We have RFCs there, and the spec as well is there, so you can go on that link. Finally, we set up a blog recently for O1 Labs. We're going to try to post pretty often, so check out the blog. And of course, all of that work is for the Mina protocol, so check them out also. Cool. Yeah, that's it. Thanks.
So I think we do have time for one question, if anyone has a question. Yes.
Thanks for the talk. I have a question about the expression abstraction. What's the objective function when you do optimizations, and does it depend on the particular proof system?
Can you repeat that, sorry?
So when you do optimizations over the expression abstraction, you said to reduce maybe number of constraints or something like that. What's your objective function? What are you trying to minimize? And does that depend on the proof system that's running?
Yeah, that's a really good question. It probably wasn't clear. It's doing things kind of, what it can do is, for example, if the expression is written out in a way where you could, for example, rewrite it symbolically to have fewer multiplications and things like that, it's doing things like that. But like tying into proof system and things like that, it doesn't do things like that. That would be provided on the proof system side, the other parts.
Yeah, we can pretty much analyze that tree and lint it or kind of warn the developer.
One last note. Kimchi is general purpose, so we're really keen if people want to use it to do a project or build something or make GitHub contributions. That would be awesome. It's something for everyone.
Cool. Thank you so much.
Thanks.